doctor Joaquín Salas Rodríguez para que él haga la intervención y la presentación de nuestro invitado de hoy. Adelante, doctor, por favor.
Andrea, muchas gracias. Fíjense que la plática de hoy creo que es muy oportuna. Justo la semana pasada se daba cuenta de que el 2024 había sido el año más caliente en la historia y fue más caliente superando al 2023, que había sido el más caliente de la historia. Una cosa interesante también que ocurrió en el 2024 es que por primera vez la temperatura superó los 1.5 grados centígrados. Depende de a quién le pregunte, pero puede ser un poquito arribita, un poquitito abajo, pero anda por ahí, por unas centésimas, ¿no? Esto es significativo porque ese es como un límite que los científicos habían pues propuesto como un límite seguro. Pues quién sabe que venga en adelante, pues que la temperatura precisamente fluctúa y quién sabe que venga, pero este es el escenario que, por ejemplo, estaba en los acuerdos de París. Y se da justo en el contexto de que mientras hablamos, pues hay un incendio que ya ha estado por 7 días por allá en Los Ángeles y digamos, parece muy lejano, pero por ejemplo, yo tengo un hermano que vive en Los Ángeles, ¿no? Entonces, creo que es muy oportuno esta plática en términos así como del contexto que estamos viviendo. Y creo que yo estoy eh, absolutamente contento de tener el día de hoy a David Rolnick. Es un orgullo tenerlo por aquí con nosotros. Déjenme leo su CV. Pues David Rolnick es Assistant Professor y Chair de Canada CIFAR AI. Canada CIFAR AI es un conglomerado que hay de científicos en AI en Canadá. Hay 400 de estos nombramientos y él particularmente está en la Escuela de Ciencias Computacionales de McGill, en la Universidad de McGill. Y también él está en lo que se llama el Mila Quebec AI Institute. Este Mila Quebec AI Institute fue fundado por Joshua Bengio, que fue uno de los fundadores de este movimiento de inteligencia artificial de Deep Learning. Fue fundado en 1993 por él. Muy importante, David fue cofundador y ahora dirige lo que se llama Climate Change AI. Esta es una organización global que trata de motivarnos a quienes trabajamos en inteligencia artificial, en machine learning, a trabajar en cuestiones de inteligencia artificial y cambio climático. Y para darles una idea, este año tuvo una convocatoria para presentar propuestas de investigación. Cada propuesta la financiaba con hasta $150,000, con un fondo que tenían de 1.4 millones de dólares. A tiempo él es codirector científico de algo que se llama Sustainability in the Digital Age. Este grupo es interesante porque ve cosas relacionadas con pérdida de biodiversidad, cambio climático y vulnerabilidad humana. A tiempo codirige el Global Climate Change on AI and Biodiversity Change, que está más enfocado en biodiversidad e inteligencia artificial. David recibió su doctorado en matemáticas aplicadas por parte del MIT. Él es un fellow de AI 2050. Este es un fellowship que otorga Eric Schmidt, que ustedes lo recordarán por su rol en Google. Y anteriormente pues fue becario para su postdoctorado en matemáticas por el NSF y también durante sus estudios de graduados. Y también fue becario Fulbright, que es una entidad del Departamento de Estado que beca a gente estadounidense que vaya fuera de Estados Unidos y gente de fuera de Estados Unidos para que pueda llegar a ir a hacer trabajo de investigación en Estados Unidos. Muy importante, en el 2021 fue nombrado por el MIT Technology Review y apareció en su lista de 35 innovadores de menos de 35. Este es un nombramiento que se da globalmente y que busca a las 35 personas menores de 35 años que tienen una influencia global, son inventores, visionarios o pioneros. Y por todo eso nos da mucho gusto tener el día de hoy a David Rolnick. David, welcome very much to the National Polytechnic Institute. Thank you for being able to talk to our students, and you can take it from here.
Thank you so much for having me. It's a pleasure to be there with you virtually. Let me try to share my screen. I never get this working well in Teams, so let's see how well it works. And this is an experiment. It's working? It's working? Okay, great. Well, I can no longer see you. This is one of the things I hate about Microsoft Teams. So you're gonna have to shout out if anybody has their hand raised or anything is going wrong. So please interject if there's something going on. So thank you for that wonderful introduction. As you said, I'm a computer scientist or mathematician by training. I'm now a computer scientist, and I focus on using the skills that I have, the tools that I have at my disposal to work on tackling one of the biggest crises that the humanity has ever encountered, climate change. I don't think climate change needs very much introduction. We're increasingly seeing its effects, and they're becoming both more frequent and more severe, depending on where you are. Everything from fires to flooding to intense heat to melting ice, melting reduction in water available for crops, and many downstream effects on human society and ecosystems around us. And we are very far from tackling climate change. Here is a somewhat dispiriting graph. This is where we need to be if we are going to come close to the 1.5 degrees target set in the Paris Agreement. This is becoming increasingly impossible. These are current policies. We are very far from this, we're very far from this green line that we need to be at. This is where we would be if we were actually following the pledges under the Paris Climate Agreement, which is closer, but still not nearly far enough. There was a lot of work to be done. I'm often asked if it's too late to tackle climate change. And indeed, it may be too late to get to this 1.5 degree target, but it really isn't too late to tackle climate change because every bit of effort that we put in makes a difference. It's not an on-off switch. We know that millions of people are going to die as a result of climate change, but we get to decide how many millions that is. And every kind of tool is needed. Computer science, machine learning, AI are not the most important tools for tackling climate change. They're the tools that I personally have, and so that's what I'm using. That's what I'm going to talk about today, but I do encourage folks, I know folks in the audience are coming from many different backgrounds. I'm not trying to say that you should all be using AI to try to fight climate change. Very far from that. So I guess I should start out by saying what is AI, especially since it's a term that gets thrown around a lot now. It's a very broad term. It means any computer algorithm that makes predictions, recommendations, or decisions on the basis of a defined set of objectives. That's an official definition from the OECD AI principles, just rephrased slightly. Within that, there is something called machine learning, which is particular kinds of AI algorithms that can infer patterns from data. There are other AI algorithms that are told explicitly what to do and don't infer patterns from data. They are symbolic AI approaches. Machine learning includes random forests, Bayesian methods, and deep learning, which is also called neural networks. This area has become particularly popular in recent years. And it includes things that you see in the news, like the AI that's being used in self-driving cars, the AI that's being used in ChatGPT, and many other things. But AI is a lot of many different algorithms, and what I'm going to be talking about today is none of that stuff. It's not self-driving cars. It's not ChatGPT. Why is AI useful? What kinds of settings can AI be useful? Well, broadly speaking, AI is very good for performing straightforward tasks quickly and automatically. A good rule of thumb is if a human can do it quickly, but it's kind of boring, then an AI algorithm can often do it. If a human can't do it, then you might not want to even try for an AI algorithm to do it. AI algorithms are also very good at finding subtle patterns in large data sets, especially machine learning algorithms, because that's all that they do. They find patterns in large data sets. And AI has many weaknesses. It's very sensitive to data, especially machine learning algorithms are sensitive to data since they need to learn from that data. And if the data is bad or has biases in it, then the AI algorithms will perpetuate those inaccuracies or biases. The algorithms can't think outside the box, generally speaking. There's no like intuition. As an example of both of these things, you can train machine learning algorithms to play video games very well. But if you change the background color on the video game, then the algorithms break, or at least the standard ones do. That's because they were used to data that looked a certain way, and when the data changed, they weren't able to think outside the box in a way a human could do. So very powerful, but also very brittle in certain ways. And generally, machine learning algorithms at least can't explain the reasoning, why a decision is being made. It's generally just, this is the decision. This is the answer. And that's either right or wrong, but you don't get to work out why that's the case. Okay, so this is a very fast introduction to AI. Now, how is AI relevant to climate change? I'm not going to go into all of the many different ways that that's the case. We wrote a big paper analyzing lots of different ways that AI can help in tackling climate change, from climate modeling to interfacing with heavy industry and manufacturing, transportation, buildings and cities, agriculture, forestry and other land use, electricity systems, generation and distribution and transmission, and adaptation in many different ways to how climate change is affecting ecology and how climate change is affecting our built environment and many other things. I'm going to talk about 5 overarching themes which we see across these many different areas and sectors, with some very quick examples. But then I'm gonna dive into some more detail on some of the work that we do in my own group. But if you're interested in more detail on any of these, do check out this big compendium paper called "Tackling Climate Change with Machine Learning." I'll give some more resources at the end too. But the overall themes that we see for how machine learning and AI can help advance climate action is really fitting into many of the other ways that people are working on tackling climate change. Machine learning is one piece of many different things. Not the most important piece, but can be useful in many different ways. Distilling raw data into actionable information. Taking big data sets and turning them into recommendations for policies, or not exactly recommendations for policies, information that's useful for policies or in other kinds of decisions. For example, if you take satellite imagery and you work out how much deforestation is happening in a given area, where is that happening in real time? A human couldn't process all of those images fast enough, but AI algorithms can scale that up. Or looking at crop yields, trying to understand where crops are around the world and how is that changing as a result of different weather patterns. Taking that big data set and turning it into a smaller, more actionable piece of information that people can then decide how to act on. Improving operational efficiency, taking a complicated automated system like a factory or the electrical grid and helping it run more effectively. So for example, taking the manufacture of steel or cement and increasing the energy efficiency by through optimization algorithms involving AI. Forecasting. So taking a system where there's data over time series, and predicting what's going to happen in useful ways. So for example, in order to minimize wasted electricity and be better able to integrate renewables like solar and wind, we need to know how much power is being produced at any given moment, how much power will be produced, and how much power will be consumed. So we can do forecasting, minute by minute forecasting of how much power is going to be produced over the next hour, using AI to help make better forecasts as the amount of power available varies, as solar panels and wind turbines change with different amounts of different kinds of weather. You can also forecast how much power people are going to be producing, people are going to be consuming. Time-intensive simulations are really ubiquitous across climate change. In particular, modeling the Earth's weather and climate is a really big physics problem. It involves lots of coupled differential equations, and we understand the physics very well, but solving those differential equations can take a really long time. So standard physics-based simulations of the Earth's climate and weather are very slow. AI can help speed them up. And then scientific discovery, the process of innovation in science, sometimes can have useful tools from AI to suggest new materials for batteries, for solar cells, other kinds of processes that are needed in order to help make the energy transition faster. Okay, let's dive into some examples. But before I go quite into the examples, I want to talk about sort of what is meant by AI in the context of climate action. Because there's a lot of work being done on AI and machine learning, and most of it is not that helpful from the perspective of climate change. In fact, we'll see at the end that a lot of it is harmful. It's actually making climate change worse. So with all this work being done in AI, why aren't we able to just like use these fancy AI tools and immediately solve all these problems in climate change? Well, it's because A, the problems are hard, and B, we're actually building oftentimes the wrong AI and machine learning systems. Much of machine learning is this kind of machine learning, where there is a focus on solving very general problems using some standardized, stereotyped, benchmark data sets. You may have heard of things like ImageNet or MNIST, CIFAR 10, the OpenAI GYM. These are all ways that people test machine learning and AI algorithms and designed to test general functions that those algorithms could have, and test them against some numerical metrics like how accurate is it at classifying images, etc. And the goal is, by having a really, really big data set, sometimes as big as the whole internet, you can build an algorithm that works for all these different problems. And that sometimes is useful. But if you end up trying to use it in many different specific real-world use cases, you'll find that these kinds of algorithms actually don't work that well. These kinds of machine learning algorithms, if you use them out of the box, they will often underperform relative to what you would think, given that they are like they're the distillation of lots of really good research effort, but they don't immediately work in many different settings. And that's because by designing for sort of general purpose use cases and trying to solve all the problems at once, you often solve none of the problems. You often end up coming up with something that sounds great and works well in stereotyped benchmarks, but doesn't actually work well in real world use cases. And so we need more kinds of more AI tools that were driven by specific use cases, as concrete as possible, diving into a real world problem and working out what's necessary in that particular problem. That problem might require a small algorithm, can be scaled very effectively across a very big data set. It might need a problem that incorporates physics in a way that is relevant to the particular application. It might require interpretability, understanding how the algorithm works. And in order to solve these kinds of problems, we can build in as much knowledge as we have about the problem at hand. Rather than designing some general purpose AI system that's designed to solve all the problems, we can build algorithms that are designed to solve very specific kinds of problems. And this is often what's needed in order to make progress in climate and various other ways that people use machine learning and AI, like in healthcare. Oftentimes these two areas work together. It's not like we need just this side without this other side, but we often need to think in terms of both sort of blue sky innovations and in AI and machine learning and in application-driven methods that are really tailored to the specific tasks at hand. Some of the challenges which need to be addressed, and here I'm speaking to maybe more the computer scientists in the room, many of the challenges that you run into in these real-world tasks are very interesting challenges, from a computer science research standpoint, things like out-of-distribution generalization, interpretability, lightweight models, physical constraints, as I mentioned, limited label availability. You don't have a lot of labels on your data, multimodal data, and other things. If you don't know these terms, it doesn't matter. I will go into some of them in the next slides. But just to say that basically there's room for both integrating machine learning into different problem spaces and also new machine learning that tries to tackle the particular challenges that we face in real-world use cases. So let's look at some examples now. The first example I want to touch on is from our work in remote sensing, trying to use satellite imagery to uncover useful properties of land use, forests and agriculture. And the motivation here came from our partnership with stakeholders like NASA Harvest and the European Space Agency's World Serial Project. Many of the most severe impacts of climate change come from its effects on agriculture. And if you are a government trying to ensure that you're going to be producing food, then you need to understand where crops are and how they are being affected by different weather and climate patterns. And having this data at scale is actually really difficult. Many governments around the world do not have the ability to just know where all the crops are, because that takes a lot of work. And satellite imagery can be one way to work out where farmers are planting what and how those crops are doing. So NASA Harvest and World Serial work with governments around the world to provide data using algorithms that can process satellite images and find information about crops. So this was a map created, for example, by our partners for the government of Togo, pointing out different crops across the country. But how do you actually get those kinds of maps? How do you build them? Increasingly, people are trying to use machine learning to process remote sensing data at scale, but there are many challenges. One is labels. Machine learning needs data, and it often needs labeled data. Data that says not only this is a satellite image, but what's in that image? Is it wheat? Is it corn? Is it something else? Here's some data from our partners at NASA Harvest, and you can see that it's very concentrated in certain areas. The orange data is where we know actually what kind of crop it is. That's not very many places around the world. And so you have very sparse labels often. You also have some challenges like might be an image. It's kind of poor resolution, right? I wouldn't be able to look at this and know what's going on. But also, you actually have only one label for this image. You have only this single pixel right here, like what's going on there. That's because somebody went to the field and actually looked. But you don't have very very dense labels. You don't have labels on every pixel, which many machine learning algorithms would expect. And then you also have a limited computational budget. The stakeholders who are using these algorithms often don't have access to massive server farms. They often don't have access to GPUs at all, which are used in much of modern machine learning in order to scale up the use of large machine learning algorithms. And so you have to have algorithms that can work very well with sort of somewhat limited computational hardware often. That's the case, by the way, everywhere in the world. This is not a problem that is faced by like especially poor countries. Canada's environmental agencies do not have access to GPUs. So if you were trying to use standard methods-driven machine learning techniques, it would sort of fail completely because you don't have enough labeled data. The data isn't labeled in the way you would expect, and the normal approaches are really, really big, and they don't work with limited computational budget. So let's think about application-driven machine learning paradigm. We're going to try to optimize here, not just for sort of standard accuracy metrics of did we label the right crops. We're also going to try to have our algorithm have application-specific metrics for success, which is how small is it? Not just how accurate is it, but how small is it? How well does it scale? And we're going to try to integrate domain knowledge about the kind of data that we're working with. So we're not going to use general purpose algorithms. We're going to use algorithms that are specifically for satellite imagery, and sometimes even for this kind of satellite imagery. We're going to build in specifically geographic structure, because satellite imagery has location associated with it, and there's actually a large amount of unlabeled data. Even if we don't have labels for all the data, we have large amounts of imagery for places with no labels at all. And we also have many different sensors and different kinds of features. So if you have a satellite, it has many different sensors on it. It doesn't just have RGB channels, which are sort of standard in any digital image. It also has other kinds of sensors, and there's other information about the place on the ground that you can then add in addition to just the image that you're looking at in RGB. So we'll get to how we use all this in a moment, but I just want to first say that actually all of this information and all of these challenges occur not just in monitoring agriculture, but also in tracking tree species, in analyzing fuel moisture content, which is a factor in predicting wildfire risk, in algal blooms, and in many other different contexts, which are all related to climate change. So by tackling the particular challenges associated with this one problem, we're actually going to end up having an algorithm that's useful in many of these cases because there are shared challenges. And we're going to find that our algorithm is actually useful in every one of these cases. So the algorithm I'm going to talk about is called Presto. And it's already being used now by stakeholders around the world to solve lots of different challenges in remote sensing. And what we did here was we designed the algorithm to leverage both sort of powerful new machine learning techniques, but also really leverage the structure of remote sensing data and be as small as possible. So the way that it works, I realize I forgot to put in a slide here. Man, okay. So I'm gonna give you a quick explainer on the kind of algorithm this is. This is an algorithm that I have it here. No, I don't. This is an algorithm that is a data representation algorithm. So you've definitely seen data representation algorithms. They can take some complicated input data and turn it into a useful form that you can then use in a downstream application. These include algorithms like PCA, which takes some complicated data and reduces the dimensionality down to a few numbers that you can then analyze in lots of different ways downstream. And this is what we're going to do here. We're going to take some complicated data and we're going to turn it into something that is useful for many different applications downstream. And the way we're going to turn it into a useful compressed form is by using deep learning. So what we're going to do here is we're going to take in many different parts of a satellite image. We're going to take in the RGB data, so what it looks like in the visible spectrum. We're going to take in synthetic aperture radar, which gives you like a sort of a different perspective on the data. You're gonna, and that's another sensor on various satellites. You're gonna take an elevation map. You're gonna take precipitation, and you're gonna take this thing called dynamic world, which is some notion of like what type of land cover there is. Is it forest? Is it desert? Is it rock, etc. And all of this information is available for the whole world for free. And you're going to take all of that and you're going to stack it together and you're going to throw it into our algorithm. And I'll tell you in a moment what we do with that. But you're also going to take in the geographic location and the time, because that's also information that you have access to. And then the critical thing here is you are going to, this is a masked autoencoder. It's a kind of deep learning algorithm where you do not need labels at all. Instead, what you do is you throw out bits of the input and then you try to reconstruct them. And I'll say in a moment why that's useful here. But suppose you have access to all this data. You can throw out bits of it. You can say, okay, I'm going to try to reconstruct the elevation map from all the other things, or I'm going to throw out everything except the RGB data, and I'm going to reconstruct all of that. And you're going to do that randomly across lots of different ways of taking out pieces of your input. And at the end, you've got an algorithm that is able to take in lots of different kinds of data and predict other data from that. In some sense, the data is its own labels, because you don't have access to some person that's gone through labeling this data, but you have an algorithm that can take some set of data and reconstruct other kinds of data from it. Here's an example. This is what it looks like, what a particular place looks like in RGB data. And this is the algorithm reconstructing that from the other kinds of inputs that it got, like elevation, precipitation, and so on. it can reconstruct what this place looks like without ever seeing an image of this place. And that's because the machine learning algorithm was trained. It was given enough data that it was able to learn how to do that. Now, why is this useful? Well, once you've got the algorithm that's able to work with whatever input data it's given and encode that in some form, and then turn that into a fully reconstructed version of the input, you can chop it off in the middle and take this compressed form of the data and then distill that into many different outputs. This is called representation of the data, or an embedding of the input data, and that can be used to do whatever you want, basically. You can train linear regression on it, a random forest, k-nearest neighbors, very simple algorithms that will give you a meaningful output. And that could be done task 1, something to do with forest, task 2, something to do with agriculture, task 3, something to do with fires, many different tasks. And you can use it in lots of different contexts. I'm going to go quickly over these numbers, but basically what this shows is we can use this algorithm in all of those settings that I showed you before, because it is able to capture important information about the structure of satellite imagery. It can take data on satellite imagery, and because the structure of satellite imagery has all of these things aligned, it is used the data itself as a label that enables it to learn meaningful information about the satellite imagery. And then when you need to actually use it in practice, you only need to give it a few labels and a very lightweight algorithm in order for it to be useful. I won't go through some of the details here because, again, I think they're a bit more technical, but I'm happy to answer questions on them if people are interested. I'm also going to skip over, in the interest of time, since I've been told I should be maybe 10 more minutes. I'm going to skip over the second application, but this application is in basically enhancing the resolution of the predictions of global climate and weather. If you take a fuzzy image like this, you can make it sharper, and you can do that using AI systems. Again, I'm not going to go through the details of it, but I'm happy to answer questions about it. I want to touch on one more application, though, and this is in biodiversity. And I want to give an example here first of how often AI is designed without users in mind. Machine learning as a field often uses big benchmark data sets like ImageNet to evaluate models and design algorithms for particular applied settings. And these benchmarks are often designed just from internet data, and they're designed by people who don't have knowledge of how they're going to ultimately be used, because they're often designed either by members of the data is pulled by members of the public, like from Amazon Mechanical Turk, and the problems are designed by computer scientists rather than by people in whatever the area of application might ultimately be. And so in the case of ImageNet, it's this big data set that's used across computer vision and AI. And about a quarter of it is wild animals. But none of the people who built the data set actually had any knowledge of wild animals. And so we worked with some ecologists, experts in particular groups of animals, to analyze the 27% of this data set that is animals. And we found that a hefty number of the images are just flat out wrong. And a hefty number of the categories don't really make sense. They overlap with each other. So it is an example. One of the categories in this data set is like mongoose, a group of African mammals. And then another category is meerkat, which is a kind of mongoose. And then actually what these algorithms are being designed to do is they're designed to classify images as various different things. Is it a table? Is it a chair? Is it a meerkat? Is it a mongoose? And that makes no sense because meerkats are a kind of mongoose. And actually most of the images of mongooses in the data set were meerkats. So this was a task that made no sense from the perspective of actually what these images show. And this is how we're designing our algorithms in order to solve real-world challenges, sometimes in actually classifying animals. The species were also heavily biased towards the United States because it was designed by folks from using internet data, and internet data is known to be heavily biased towards the United States. I can go through an example here, but you can see like this is a variety of different birds that are all called jays. This is what we have in Canada and the US. This is a species of jay that is more common in Mexico, certain parts of Mexico. This is a species in Europe. This is a species in Sichuan province in China. The vast majority of the data was this one, which is only found in Canada and the northern US. So yeah, problems in the data. These are the data sets that are often being used to pick the state-of-the-art algorithms and to design for real-world applications. So we really need to have a better pipeline for designing the AI systems that are used across society. Fortunately, in the case of biodiversity data, we actually do have better data sets. People often use data sets coming from this citizen science database called iNaturalist, which is used around the world. There is still a bias significantly towards the global north. This includes data labeled by experts on everything from crayfish to mushrooms. And it is being used widely in order to help people identify images of wildlife. You can get apps on your phone, including from iNaturalist itself, that will help you identify species using AI. And we're working on particularly applications using data like iNaturalist data in order to design automated monitoring systems that can be out in the field and gather data about biodiversity at a scale previously unimaginable. And we're working on insects, which represent half of all global biodiversity. Here you can see this is our system being set up in a particular reserve in the middle of the Panama Canal. This is called Barro Colorado Island. It's run by the Smithsonian. The way that the system works is it tracks insects using this light, and then at night you get thousands of insects that come here and they're photographed automatically. This thing is solar powered and it can be put out in a dense rainforest or in an open area for months at a time, gathering lots of data. And that data is then processed using AI to get an understanding of what insects are in the environment. And again, half of all biodiversity is insects, and insects are precipitously declining in many places. And we don't really know why or how to stop it. This is having huge effects on agriculture, on biodiversity more broadly. Obviously, a lot of stuff relies upon insects. And so this is how our algorithms work, or like at a very high level, how they work. They're taking in some data coming from databases like iNaturalist and museum collections, and they are learning how to pick apart different species. And you can see tracking individual species on a sheet like this. You can gather data for very large areas and process it at a scale previously unimaginable because there just aren't enough people with expertise to be able to do this. We've run into a lot of challenges, of course, everything from coatis coming and eating the insects at the trap to the large number of species that are just new. 80% of all insects have never been discovered. And so we're actually building algorithms now that can suggest this might be a new species. And that, we hope, will help not just uncover trends in insect biodiversity as a whole, but try to uncover the 5 million new species of insects that are disappearing before we've even named them. This is obviously a collaboration with lots of different organizations. Here are some of them. I've touched on many different examples here, but I want to leave some time for questions. And before that, I want to sort of talk about overall lessons. I want to emphasize, machine learning and AI are not silver bullets. They're only relevant sometimes in tackling climate change, and they're only relevant in conjunction with other initiatives. So in Presto, we worked with the organizations that are already looking at satellite imagery, and they had specific challenges that we were trying to address. Same thing with the automated monitoring of insects projects, and same thing in our climate science algorithms. We work with the relevant companies, researchers, or government agencies in order to find the right challenges and make sure we're solving the right problem. The high impact applications are often not flashy. Self-driving cars are probably going to make climate change worse. I'll talk about that more in a moment. The things that you see in the paper are not necessarily the ways that AI is actually making climate change better or making life better for people. And notably, I want to shout out, now that everybody's talking about large language models like ChatGPT, there are very few ways in which large language models and chatbots are actually helping climate change. They're definitely making it worse through huge amounts of energy consumption, but there are very few ways in which large language models have useful applications in tackling climate change. The other kinds of AI, most of AI is not large language models, and those are the kinds of algorithms that we're working with in all of our work. And then obviously this is interdisciplinary collaboration. I'm a computer scientist, but all of these projects require people with expertise across many different areas to scope the right problems, incorporate the right information, and make sure that it's actually being used. So I want to touch on what I hinted about. Machine learning and AI also making climate change worse in many ways. What gets talked about most, and is increasingly a problem, is computation-related impacts. That's energy used in computing, in powering computers, and the embodied emissions from hardware, so how you actually made the servers. That comes with both energy usage and other challenges associated with water usage and with heavy metals used in making them. I will note that this really depends upon the algorithm. So remember, the algorithms I was talking about, like Presto, that's a tiny algorithm. It has, in some cases, 100 parameters. By contrast, something like GPT has on the order of like 1 trillion parameters. It's unclear. So AI is not one thing. You can use Presto as long as you want, and you're not going to use more than a tiny amount of energy. And developing GPT uses a vast amount of energy. So AI just means a lot of different things. Not all AI is created equal in terms of computation. Application-related impacts, though, is also really important. There are ways that AI is making climate change better, but it's also used extensively to help fossil fuel exploration and extraction, as much as a 5% production boost. And AI enables all of online advertising, which is, in some cases, increasing consumption, like in fast fashion, where the advertising industry is a major contributor to people buying more clothes than is sort of needed by society. Then there are interesting cases like self-driving cars. So autonomous vehicle technology, self-driving technology actually can have positive or negative impacts on climate change, depending on how the tech is developed and deployed. Self-driving cars are expected to make climate change worse because they make it easier to drive. And so people will probably drive more. Even if each mile driven becomes a little bit more efficient, it's overall expected to make climate change worse. But the same technology could be used in buses and encourage people to use public transportation, and that could be good. So it really depends upon how you develop and deploy, sometimes even the same technologies. And I think that's what I wanted to leave you on. AI for good, which is a term that those in computer science may have heard, that should not just mean adding some new good applications of AI on top of business as usual. It means shaping all applications of AI to be better for society. And more broadly, technology is a double-edged sword, and you don't have good it's not about let's add some good applications of technology upon together with the normal applications of technology. It's like taking all of the things we're doing and making all of them better for the planet. If you're interested in more resources on this topic, I encourage you to check out Climate Change AI, which is a nonprofit that I co-founded and has a lot of different kinds of readings, different kinds of opportunities for people in the space of AI and climate change. We have that big report on tackling climate change with machine learning. We also have conferences and other events. The next one will be at the International Conference on Learning Representations, one of the major AI conferences this year. That's in Singapore. You can submit papers to it or proposals for work you might be interested in doing. Both of those are due on January 31st. So you can check that out at the website here. You can also look at all the past papers, about 1,000 of them here. We have a summer school that recurs year after year, both virtual and in person, for learning more about this area. We also have funding programs. This innovation grants program just wrapped up. Is actually, yeah, so we've funded several $1 million worth of projects at the intersection of AI and climate change. And if you had to pick one thing to I would follow our newsletter, which gives opportunities in this space, from internships to new data sets that appeared and are interesting to look at. So with all that, thank you very much for listening, and thanks to my wonderful team at Mila and McGill for all their work in this research.
Thank you, David, for this wonderful talk. It was very exciting, and I particularly like your focus on trying to solve problems, and from there take it whether they needed AI or not, and also this approach that you have where you get together with people from different disciplines to work on particular problems. I think that relates very much to what we do in this research center, and I thank you very much for bringing this to us. Please, if you have questions, you can raise your hand. You can also type your question in the box, in the message box. Pueden hacer sus preguntas en español y podemos tratar de traducirlas. David, I would like to start asking you, you are in a very unique position leading CCAI, and I would like to tell us something about how much you are making inroads into this mission of trying to get AI to work on climate change problems.
Get AI researchers and practitioners to work on climate change problems?
Right. Yeah.
So I think that there's been a lot of progress. I think that there is a cultural problem in AI. A lot of people come into other fields from AI and think, oh, my powerful algorithms are just going to magically solve people's problems. And it takes a lot of work to actually meaningfully use AI on certain problems. And when it is useful, it's often the least fancy AI. And I think that AI researchers and practitioners sometimes have a problem with that, right? Like, you want to go in and you want to use the flashiest, most complicated stuff, but sometimes like linear regression or random forest or something very simple is going to do the trick. And like, I work in my group on these complicated approaches, but they're complicated approaches which are designed because the simple approaches failed. And so I do want to emphasize that when we were working on that, I know some of the audience is not coming from a computer science background. Like, when I was explaining this Presto algorithm, you don't have to use Presto to solve most challenges that you might encounter. You could probably just use random forest. That's what people did on satellite imagery until we came up with Presto. Presto is better in certain cases, but like, the simple approaches are still pretty good. And so I think that a lot of computer scientists go in thinking, again, the fanciest things are the best, but you really need to be very tolerant of the simple things are probably going to be pretty good. Mm-hmm. Sometimes you'll need something fancy, but if you need something fancy, you need to spend a lot of time understanding the relevant problem, the relevant data, and working with people, and it's not going to be a quick solution. So thinking in those terms is definitely a challenge for many people, but yeah, it's happening. We're seeing increasingly climate change as being an area of application for AI and machine learning.
Perfect. Thank you. Natalie, I see that you have a question. Would you like to open your microphone and make the question yourself? I can read it, but would you like to go ahead? Okay. Well, okay. The question is, which are other climate change problems that machine learning hasn't been able to solve, and why they haven't been solved with these tools like AI yet?
Well, many of the problems that are faced in climate action aren't related to machine learning at all, right? Like, some of the problems are just that people have to work together with various different goals to set policies that incentivize certain forms of change. Now, there are ways that AI and machine learning can be relevant to setting climate policies. Machine learning can help in reducing the barrier to action by making it less costly to adopt renewable energy, or less costly to use less energy in certain applications, or provide information to policymakers on where deforestation is happening so that it can be appropriately prevented in cases where deforestation is illegal, or providing information on how climate change is going to affect this particular city so it can respond, or so it can be incentivized to reduce greenhouse gas emissions. But ultimately, people need to act and machine learning is not going to be a replacement for that. And then there are many settings where, even in technical challenges, machine learning is not the answer, or it's not the main thing that's needed. Like, in certain cases, you just need chemistry, or you need physics, or you need people out in the field who are measuring trees. And so there is a lot of work to be done in tackling climate change that just isn't relevant to machine learning. And then with respect to the problems where machine learning is useful, it's, as I said, I think it's tough to design approaches that work in real world settings, because fundamentally problems are hard. There's a reason we haven't solved some of these problems. Yeah, if you have a follow-up question, I'm happy to take it.
All right. We have a question from Gabriela. Gabriela, are you able to open your mic and make the question yourself?
Yes.
Okay, go ahead.
I can you answer beyond improving the accuracy of climate predictions? How can machine learning contribute to designing more effective mitigation and adaptation strategies in the face of climate change, considering the inherent uncertainties in current models?
Yeah, so I think that it's a really good question. So the different sources of uncertainty in models of climate change. There's uncertainty which comes from uncertainty about what people are going to do. And there is uncertainty associated with just the physics being difficult to predict. And machine learning can help with the second one, because, as I said, there are ways that machine learning is being used in order to help with physical simulations. There are particular pieces of physical simulations involved in the Earth's climate and weather where they're just very slow, or like even prohibitively slow to run, or where we don't have the right kind of data to input into these. So, for example, something that we're working on is trying to get to use data that exists to get better info for precipitation forecasting in parts of the world that don't have radar, ground-based radar. So that can be a way to use machine learning to help adapt to climate change, because climate change is affecting precipitation patterns. And there's inequities in who has access to the data on precipitation patterns, basically. So machine learning can help with that, like getting better data. But then in terms of actually sort of responding here, there are a lot of different ways in which society needs to adapt to climate change. And that can be everything from designing different kinds of infrastructure in the built environment to having better ideas of how climate change is going to impact certain parts of society. I think there are a lot of specific applications. I could just sort of rattle off a few. There are ways in which people are using machine learning to simulate the what's called urban heat islands, so intense heat that's found in cities. There are ways that people are using machine learning to design more robust electrical grids that will work if certain power lines go out, which is something that can happen with extreme weather in climate change induced scenarios. So you can have more resilient electrical grids. That also helps, by the way, in integrating renewables into the electrical grid. There are people who are working on machine learning and AI for simulating certain public health scenarios, the spread of various diseases, under climate change. What I talked about of monitoring crops is a major way that people are currently using machine learning to process satellite imagery to understand where are crops. That map of crops in Togo, by the way, that was used by the government of Togo to direct aid to specific farmers who are facing crop failure as a result of climate change. So it was concretely used to have on-the-ground impact in responding to climate change. So these are very concrete applications. And then when I talked about biodiversity monitoring, well, that's responding to climate change as well. One of the major reasons that biodiversity is declining is as a result of climate change. Insect populations are crashing partly as a result of climate change, and that has effects on agriculture, it has effects on forestry, it has effects on species that are even not insects. There's a famous situation in which all the birds that ate insects in a particular, in the rainforests of Puerto Rico, died out as a result of insect population collapse. So yeah, these are all different ways that people are using AI.
Perfect. I think that we are getting close to run out of time, but I don't want to let you go without asking you this. We have some other questions, but now, we have here students, master and PhD students. They are going to be the future leaders in research, development, in innovation, in the context of here, Mexico. But I would like to ask you, what piece of advice can you give them in the context that we are living? And especially
in the
from
context
the position,
in which we're
in the context that we are living with climate change, biodiversity loss, but also great opportunities.
I would think, I guess I would think about, I don't think everybody should be using AI to fight climate change. Not everybody in this room works on AI. Not everybody in this room works on climate change. Pick a problem that really matters and pick a tool that you have knowledge or experience or passion in, something that you can bring to the table, and work out how to bring them together. And it doesn't have to be the most important problem, and it doesn't have to be the most important tool. Your goal should be to find something that is quite meaningful. It doesn't have to be the most important thing. Again, machine learning AI, not the most important tool for climate change. It's what I can bring to the table. Think about what you can bring to the table for a problem that you care about. And you may not have unlimited abilities to use that tool for that problem. Many people, most people, are not researchers, right? But there are ways that you can use the tools that you have, regardless of what your job is, and steer that job towards impact on problems that you care about. And work out ways that you can do that more. You can use the tools you have, whether that is as a chemist, as a mechanical engineer, as an economist, as a writer, as an artist. Work out ways that you can use those tools to make a difference on a problem that you care about. And that is, I think, what we all need to be done more. Thank you so much for listening.
Perfect. Thank you very much. Well, on behalf of the National Polytechnic Institute, David, thank you very much for this very exciting and awesome talk. It was very inspiring, and I thank you very much for sharing it with us. And bueno, pues muchísimas gracias. Yo quisiera decirles que recordar a Jared Diamond, él decía que estas cosas de cambio climático, pérdida de biodiversidad, la vulnerabilidad humana, todas se van a resolver. Si nosotros tomamos no decisiones, si no tomamos decisiones, pues se van a resolver tal vez de forma caótica. Si tomamos decisiones, pues puede ser que se resuelva a nuestra conveniencia con nuestros términos. Entonces les invito a tomar muy buenas decisiones. Y ahora dejo esto en manos de Andrea. Andrea, muchas gracias.
Muchas gracias, doctor. Thank you very much, Dr. Rolnick, again for your time and this so interesting conference
Thank you so much.
you gave us.
Thank you so much.
Así que vamos a hacerle llegar al doctor Rolnick de manera digital su reconocimiento por su participación en el seminario de divulgación multidisciplinario de este centro. Y muchísimas gracias. Thanks again. Y
Thank you for
bueno,
having me. If you're interested in checking out the resources at Climate Change AI, I put the link in the chat.
thank you very much. Muchas gracias, doctor. Y bueno, les
Okay.
agradecemos
Yeah.
a todos su participación en esta tarde. Este sería nuestro penúltimo seminario. El siguiente lo retomaremos de manera presencial. Y para avisarles también que en un momento en el chat nos estarán compartiendo la liga para tomar asistencia. Y bueno, muchas gracias de nuevo. Nos vemos el próximo martes. Buena tarde.